The next challenge is AES-BAD-256. I did not solve this challenge during the CTF. I had to look up the write-ups later. I did spend many hours on it, and after reading the write-ups, I'm kind of frustrated. I made things a little bit more complex than they needed to be, but thankfully there's a really good write-up by the challenge author. You can see it here. Here's the URL, Seraphin, irisCTF AES-BAD-256, and a bunch of people in Discord were also talking about their solutions. But anyways, like I said, I went back after the CTF and I solved it myself just to make sure I understood it. And it is a fun challenge. I'm just frustrated I didn't get it during the CTF. Anyways, so it says, I heard that some common block cipher modes have a lot of footguns using ECB results in legendary ECB Penguin, while others are vulnerable to bit flipping and padding attacks. So I made my own that would never fail to such a technique. We're given a challenge file and this netcat port. If we look at the challenge file, so overall the challenge is this server, and we connect to the server and we can do two things. We can run a echo command or run a command. When we run a echo command, we give it some text and it'll generate this echo payload, which I'll talk about in a second, and it'll encrypt that echo payload and give it back to us. The second thing we can do is give it a command. It'll read the command. The command has to be the encrypted ciphertext. It'll decode the command and it'll do one of two things. Either it'll run the echo command, or if somehow you got it to say it is a flag command, it'll give us the flag. So our goal is to kind of do a message forgery attack. Using this oracle, we need to generate a message such that it has the command of type flag. The interesting things about this challenge, it's using a custom block mode. So normally, in AES, you're going to be using like CBC or GCM or OFB, CTR, any of the block modes. This is using a different one. I guess it's like a permutations-based block mode, and we're really going to be trying to exploit that. A couple other things of note. Normally AES block mode is 16 bytes, or block size is 16 bytes, and we are using AES with that block size. This permutation mode introduces a new block size of 256, and I'll show what that looks like in a second. The message structures. So when we ask for an echo command, we give it some input, and it'll generate JSON that looks like this. So it'll be of type echo, message, and here, and this is our input. So when I first started this challenge, I think there was a Modosano challenge, or sorry, a CryptoPals challenge kind of related to this, where you were able to actually inject, I think the challenge setup was very similar. And so at first I was trying to set input equals to something like type flag. And basically I was just trying to inject the payload we wanted. I think there's also 2 length bytes, but I was trying to inject that in. But the problem is, like, when you inject this in, JSON's going to correctly escape all the quote characters and stuff, and so it doesn't quite work. But anyways, that's not the solution. But we can see we encode 2 length bytes to the front, which are just little endian checks. This is useful because it'll actually truncate the message when we send it back to the server. So if you have garbage afterwards, it'll just truncate to this length bytes, which is necessary for the attack. Although you could probably make your way around it, but anyways. Next is, so this is the run command. So this is going to decrypt our ciphertext and check and see if it's equal to flag. So it'll decrypt it, it'll do that length check. Like I said, it's nice that it does the length checks because it'll actually chop off everything off the end. It'll decode it, and then it'll load as JSON if it's valid JSON. Oh, and it does the strict equals false thing, which could be useful, but we don't actually use it. I think other people used it because they kind of fuzzed the solution, but we actually manually construct the bytes. We didn't have to, I just had the code laying around. So we don't abuse this. Like I said, then if the command is equal to flag, we get the flag back. Cool, so that's the whole challenge. Let's look at the actual, what this code is doing. So I have this little temp file. Basically, I grabbed that line of code and to show what the permutations do. So the server is going to generate a random permutations array every time. You can see it's just a list of range 16, so 0 to 16 or 0 to 15, and then it shuffles it. If we were to give it this as our input, so 16 bytes from 0 to F, and run the permutations, it looks, oh, I already have it. I have it here. We can see it grabs each of the characters out and joins them. Every time you run it, the permutations array is different. So we can see this time it started with F, this time it starts with zeros. It's different every time. It's also important to realize that, so this is being repeated 16 times. you don't know which one of these zeros is being pulled out to make this. So it could be the first zero or the last zero or the third zero. That also depends on the permutations array. Cool, but like we can see, if we were to put in all zeros, 1, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, I'm doing something wrong. There we go. We can see that we'll just get back all zeros. And under the hood, it's still using AES, so we can still an ECB. So this will still encrypt to the same ciphertext. And that's useful because we can imagine doing something like this: 15 plus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Oops, no, I screwed that up. We want this. Doing it the reverse way. If we put 15 zeros and then 1 non-zero and repeat that 16 times, we can see we get out a bunch of zeros, and then one block will have all ones, and then the rest will encrypt to the same thing. And so using this little technique, as we go from here to here to here and record all of them, we can actually figure out, reverse engineer what this permutations array is doing, which is pretty cool. So just jumping around, we'll figure out which ciphertext doesn't match the rest. And using that, we can reverse permutations. There's also another neat little trick. Like I said, if this is all zeros and we encrypt it, we'll know what the ciphertext, again, so this will be encrypted and we only see the ciphertext out of this. Right now we're just seeing the shuffled plaintext. But because of this, we know what all zeros encrypts to. And that can be useful. So later we'll see we're going to use 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I think I missed one. We're going to use the fact that this will encrypt to, the same ciphertext over and over and over. And so we know what FFFFFF equals. When we call decrypt on this, this block is going to map back to one of the characters. So if we know that this first block corresponds to, let's say, this character, let's say originally it was an E, H, O, let's say we had some message that looked like this. If we know that this first block, because we reverse the permutations array, if we know this block maps back to this character, we'll just set this block equal to all Fs, and we'll overwrite whatever it previously was. And that's pretty much what the attack is. So let's look at the solve script. This is not too exciting. It just calls out to the server and gets back the ciphertext for some message. This is also just generating the same sort of thing, but I'm grabbing a different bytes. Not too exciting. Anyways, here's the attack. No, that's not it. So the first thing I do is I go through. Again, you can actually brute force this and just iterate through characters one by one, and eventually you'll get out the correct flag. I already had all this code because I tried a whole bunch of different things during the CTF. So I just did it the more, I guess, precise way, but definitely was not necessary. You could have just kind of brute forced this really quickly. But anyways, what I'm doing here is I'm generating the ciphertext maps for the characters F, L, A, and G. And this will be useful later. So basically at the end, I'll have something that I will know what 16 bytes of F encodes to, and I'll know what 16 bytes of, encrypts to, and I'll know what 16 bytes of L encrypts to, A and G. So like I said, we're going to be using that in a little bit. Using that trick where you put the ones in different positions, you're able to figure out what the permutations array looks like. So like I said, here I know what F and L equal to because of above. So I'm generating as a payload of like 15 Fs, and then an L, and then 14 Fs, and an L, and then an F, and then 13 Fs, and then an L, and then 2 Fs. I go through that, and I'm able to figure out where all the characters map. And so now that we have those two things, we can actually do the attack. So when we construct an echo payload, it looks something like this. So we have 2 length bits. We have a type of echo, the message, and then this was our input. What we can do is we can ask for an input of 5 spaces, and it'll send back this, but encrypted. And after this, there's actually a bunch of null bytes. Oh, I think it should be the other way. But what we're going to do is we know all of these C's are going to be pulled out. So again, this is 256 bytes long. These are all the null bytes. All of these C's are going to be pulled out, and they're going to make their own block. And then all the D's are going to be pulled out, and then all the 2s and the 7s, blah, blah, blah. So what we can do, and we have the output ciphertext of that, is we can just replace that C block with a character we control, and we specifically want to replace it with F. And we know what Fs look like. So what we're going to do is we're going to, like I said, just replace all the C's with Fs. And the reason we made this 5 spaces was so that we don't clobber anything. The flag is just going to go right in here. If it was 4, if we asked for 4 bytes, instead we're going to clobber over C, D, E, F. We'd be clobbering over these and we'd be overwriting this one. But instead, since there's a space, we're going to overwrite all 16 E's and F's. But this is good to clobber, this is good to clobber, and the rest are null bytes that are going to be truncated later because of this length check. We don't really care what happens over here. So, like I said, and then we're going to replace all the D's with an L, and then we're going to replace every E with an A, and then we're going to replace every F with a G. Yeah, and that's the attack. So when we're done, this will also save flag here. And then, down somewhere way down there, it'll be flag again, and then, a bunch of null bytes and then flag again. And that's the attack. So this is just constructing the attack. It's nothing too exciting. We're getting that echo payload, so that original payload with 5 spaces. This is the ciphertext, so this is 256 bytes encoded as hex, so it's 512 bytes. We're grabbing the position of E. So again, we had to reverse engineer that permutations array. We don't actually know where, so it's position C, OXC. We don't actually know where this is, but thankfully reverse engineered the permutations array for this specific run, and we know what block corresponds to that position. So we can reconstruct the block. Basically, we're just kind of splicing out whatever. Right now, there's like E and then some other garbage. We're going to just delete all that, and we're just going to put a bunch of Fs in there. And so now every C character in our decrypted array will just be the character F. And then we're going to do that for L, A, and G. And then we'll have some final payload. We'll send that back, and we should get back the flag. So if we take a look at what this does, Python 3, solve.py. Cool. So this is that CT map I was saying. So 16 bytes of F corresponds to this ciphertext, L, A, and G. This is the permutations array we generated. So this is what the remote server permutations array looks like. This is our final payload. Again, we don't really know what this is because it's all encrypted, but we basically just spliced out. So somewhere in here, yeah, this is F corresponds to this block here, and that's what we spliced in. We also took in an L, we spliced it in here, and we took this A block, we spliced it in here, and somewhere, there's a G block somewhere in there. Cool. These are debug messages from the server. Normally we don't get this type of feedback, but we're running it locally, of course. And this would obviously work remotely too. Anyways, some length checks. This is the decrypted message that the server received. So it received our hex ciphertext, it ran decrypt, and I'm just printing it out. And so we can see we have 2 length bytes, so a space, so this is 32 and then 0. We have type flag, message. And so we can see we were successfully able to overwrite this. So normally this says type echo, and our message, this was all spaces, but we were able to overwrite every C character is now an F. And we can see there's Fs down here, flag, 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 flag. So yeah, our attack worked. We can see start. This is our final command, and then it runs the command and we get back the flag. So again, not a terribly difficult challenge, as long as you know what you were doing. I'm frustrated I didn't get this in the CTF, but that's okay. It was a fun challenge, and thanks to the challenge author.